So hello everyone, welcome to our next recitation on Mechanics and Materials 1. We have also 4 exercises today to look into them together. This is the first one. In this figure, you have a bar here, BOC. At the end of it, or a beam if you like, at the end of it you apply the force P upwards, and 2 members, OD and OG, and both of them are 2-force members, obviously, because they have only 2 forces at their ends, are also connected to this in order to keep it in place. Now, the material properties and the dimensions of each of these bars or members are given. So this is, let's say, E1, L1, A1. So this is member 1. If you want, this is member 2. Determine the magnitude and sign, tension or compression, of force in each of these 2 force members. All right, so as always, we start with our usual equilibrium equations, and we will see that this is a statically indeterminate system, so we do something a little bit more than that. But let's start with equilibrium. If you split this system into 2 systems, let's say we split it into the beam, BOC, and then the second system, DOG. So for the first system, what you will see is something like this. You see a beam. At point B, you have some reactions which we do not want to calculate them. You can if you want to. At point O, there would be a force, which is the reaction that you would have from the 2 members attached to it. Let's call that FO. And at the end, you have this force P upwards. Now, pay attention. I drew FO downwards because you can kind of imagine, if you think of this member and you apply a force upwards here, downwards here, it's hinged, you would need FO to be downwards, right? So it makes sense. Do not get confused with these 2. We will talk about it, how it is going to be distributed among the 2. That's a different question. But for the first part, for member BOC, you can write equilibrium of moments with respect to B to be 0, and then we can assume counterclockwise to be plus, and then with respect to B, obviously you have the length, which is 2L times P, that would cause a counterclockwise moment, and then you would have length L times F, that would cause a clockwise moment. So you write your equilibrium here, and you get 2L times P with a plus sign minus L times F is 0. So F, or FO if you like, is 2P. Okay, so this is the first part of the problem. So we know that force is 2P. But what we want to know now is to look into this system. And it's a very, very simple problem if you think about it, as we usually did before. So think about it this way. You have this member. We solved something very similar to this. We solved it horizontally. This is exactly the same thing vertically. So now this is our member with points G, O, and D. By the way, pay attention that this is just one member, right? I mean, this is one beam. These are 2 different members. Okay, so point O here is a hinge. Okay, so, all right, so if your force FO is downwards, 2P, that means in this system you would have its reaction. So you would have a force that is upwards, 2P, okay? So in this green system, the FO that you would have would be 2 pi upwards, because it's the reaction of what we had previously. Now, you can imagine if you have a force on this structure here, and that force is upwards, then you would basically cause two downward forces here, let's call them FD and FG, to compensate for that. Now, if these two members, they had similar dimensions and areas and material properties, obviously we would expect these two forces to be equal, okay? But because that's not the case, we need to basically go to our compatibility equation to solve this system. So this is statically indeterminate, right? Okay, so again, for this system, we will write our equilibrium. Let's say sum of forces is 0, and then again, if you assume upwards is positive, you would have FO minus FD minus FG 0, which gives you FD plus FG equals FO, which is 2 pi. Okay, so this is your equilibrium equation, or equation 1. But as we just discussed, because this is statically indeterminate, we also need compatibility. So compatibility. Now, to write compatibility, it's kind of conceptual. You can write it any way you like. You can, or you should, however, think of its, let's say, conceptual meaning, right? So compatibility basically means whatever change of length you get in the member OD, you should get exactly the same in member OG, okay? But think about it. If you apply a force P upwards, this thing would go upwards, right? So you would have shortening here, and you would have elongation here, right? So there would be a sign difference. Does that make sense? But the amounts, the magnitudes should be equal. So in that sense, if you want to just write it, let's say, conceptually, again, in this particular example, you can simply say, well, compatibility basically means delta OD plus delta GO is 0. Okay, again, one of them is plus 5, the other one is minus 5, it should be 0. So that would be your second equation. On the other hand, for this compatibility, if you want, you can always also think about it this way. These 2 points, they are fixed, right? So you can always think that because you have 2 points fixed, the relative displacement between them is 0. So delta D with respect to G is 0, which is delta D with respect to O plus delta O with respect to G is 0, right? So it's the same equation. Okay, so if you want to kind of look at it less intuitively, you can also write it like that. In any case, you have now your compatibility equation, you have your equilibrium. All you have to do is to insert their corresponding values with respect to the forces for deltas. So remember, delta was PL over EA. So this is our magic formula, right? So that means in each of these members, you can write this. But remember, when we write here P, I'm not talking about this P, obviously. This is internal P, right? So what we need to do is to cut these members to calculate their corresponding P, or corresponding internal force. Now, in this member, that corresponding internal force is minus FD, because it's under compression. You can actually see it here. And in this member, that internal force is plus FG. Okay, so that's all you have to do, which makes perfect sense here. Remember, it's not very surprising. We kind of expected these two to have different signs. So in the first member, you would, let's say here, you would say it's minus FD L1 divided by E1 A1. And for this one, that would be plus I put a plus here to make it even more clear, Fg L2 divided by E28 is 0. Okay, so from this you can immediately get the following relation. Fd is Fg times L2 divided by L1, A1 divided by A2, E1 divided by E2. All right? So again, this is equivalently our second equation, but this is looking nicer now because you can immediately relate this to our first equation. It's not in terms of delta anymore, it's exactly in terms of forces, and that's exactly what you are going to do. So what you want to do is to go back to this equation. Remember we said Fd plus Fg is 2p. Instead of Fd, I'm going to write this. So I would write Fg times that thing, which is L2 A1 E1 divided by L1 A2 E2. Okay, that's basically Fd plus Fg is 2p. So that immediately tells you that, let's say, Fg times 1 plus L2 A1 E1 divided by L1 A2 E2 is 2p. And now you can immediately establish a connection or a relation between Fg and p. So let's say this would tell you it's Fg equals 2p divided by, this bracket. Or if you simplify it a little, you get Fg equals 2p L1 A2 E2 divided by L2 A1 E1 plus L1 A2 E2. Okay, which is pretty nice. Remember, we said if these values are identical in both beams, we would expect kind of 1/2, so that force to be equally distributed. So you can imagine if both beams are identical, then they will cancel out. So you get a 2 here, and then the force 2p, it would be basically compensated by p in each of the members. So each of them would carry p, and then this would carry the whole 2p. But if they are not identical, this is the relationship you have, and also you can immediately get Fd from the relationship we had before. So Fd would be 2p L2 A1 E1. You can also compare the two relations. They are not too unrelated. So A2 E2 plus L2 A1 E1. So if you look at the denominators, they are similar. It's just that the nominators, they kind of do the opposite thing. So obviously, if you add them up, you get 0. You get 2p. That's that. The only thing that we didn't do is that, when I explained it, I said that this is compression, that's tension, but we didn't clearly specify that. So in your exams, or if particularly here in the question it asks you, you should identify if it is compression, tension, you should basically do that. So let's write it here clearly. This is compression, and this is tension. By the way, the fact that I'm saying it's compression and it's tension, it is partially related to the picture that we see, but it's not the whole story. I mean, after solving this, if Fd, here, if Fd came to be a negative value, that would have changed the story, right? So But now we can confidently say that's compression and that's tension based on, the force P, okay? So the FG, that's the lower one, so that member OG basically is under tension, and member OD under compression. All right, so that's that. Is that clear? Okay, so we go to the next exercise then. All right, this is a very, very nice exercise. Two different types of materials are sandwiched between three identical plates. So you have these plates. Let's say these are rigid plates if you want. And we have two different materials between them. They have different thicknesses, and they have different properties. So material 2 follows this graph, stress-strain graph, and material 1 follows this stress-strain graph. Pay attention, the stresses here are shear stresses, and the strains are shear strains, okay? Which makes sense because in this particular example, we apply also a shear loading. So we don't want to confuse you. It's a purely shear type problem, and we want to study its, let's say, its behavior for shear. Okay, so you apply a force V here. The first thing you are asked to do is to determine V if delta is 13 micrometers, okay? And delta is this, okay? So delta is the amount of displacement you can cause by applying that V, okay? I'm gonna enlarge it a little more. Does that make sense? Okay, so determine V if delta is 13 micrometers. So if delta is 13 micrometers, what should we do? We need to compute shear strain for each of these graphs or for each of these materials. So you need to compute shear strain. And remember, shear strain is basically that delta that you apply divided by height, okay? So height here is height 1 if you want, and that's 4.2 millimeters. Height here is height 2, and that's 2.7 centimeters, sorry. Okay, so we calculate this gamma 1 and gamma 2. These are the shear strains. From the shear strains, you calculate shear stresses, okay, because you have these graphs. If those shear stresses are smaller than the yield stress, and these two materials, they have two different yield stress. If they are smaller than yield stress, it means everything you have done is correct because it's elastic. If not, then you need to repeat that properly. And that's exactly the goal of this example. In this part, as we will see shortly, everything is elastic. In this part, something more exciting is happening. All right, so let's start with part 1 or part A. If delta is 13 millimeters, again, you calculate shear strain in the first part. That would be delta divided by height of the first one. In this case, what was it? It was 13 micrometers divided by height is 4.2 centimeters. Pay attention, what we get is basically dimensionless. So it would be 3.1 times 10 to minus 4, okay, which is less than 7 times 10 to minus 4. Okay, so we are here, and we are less than 7. So we are somewhere here. So we know if you calculated shear stress, it would be less than the yield stress, okay, which is here, which is 60. Okay, so we are fine, and we can actually calculate it. So now you would say tau 1 is G1 gamma 1. G1 itself is 60 divided by 0.0007. So G1 is 60 megapascal divided by 7 times 10 to the power 4, which gives you 85.7 gigapascal. Okay, so that's the shear modulus of material 1. So here I'm going to write this for simplicity. So G here would be 85.7 gigapascal. In the second one, G is also 45 divided by 0.0009. And if you do that, you get 50 gigapascal. All right? So now from this, you can calculate tau 1, which is 26.57 megapascal. And as we expect this, it's less than 60. Which was the yield stress. So tau 1 is less than the yield stress for member 1. Okay, now we repeat exactly the same thing for the second material. So gamma 2 shear strain in the second one would be delta divided by H2. That would be that 13 micrometers divided by 2.7 centimeters. Now that gives you 4.8 times 10 to minus 4, which is also less than 9 times 10 to minus 4. So that's that. So we expect our tau 2, which is G2 times gamma 2. And now G2, we know it's 50 gigapascal. Okay, so this 50 is basically 45 megapascal divided by 9 times 10 to minus 4. Okay, so that's tau 2, and then tau 2 would be, or shear stress in the second one would be 24 megapascal, which again, it's less than the yield stress in member 2, which was 45 megapascal. Okay, so now because everything is elastic, these solutions are acceptable as the shear in the member. So all you have to do is to calculate V for this delta. Now V is, it's basically a stress times area, right? And the stress is tau 1 plus tau 2. So it's tau 1 plus tau 2 times area. Now, area of that slab in the picture, the dimensions are given. Length is 15 centimeters, and there is a width inside the plane, basically, and that width is 3 centimeters. So that gives you the area where you have these shear stresses distributed on, and if you multiply them by that area, you get the shear force, V, that you need to apply to get that. And, okay, so the area is, let's say 30 millimeters times 150 millimeters. And if you calculate that, V would be 227.6 kilonewton. Okay, so this is the answer to the first part. It's 227.6 kilonewton. All right, so that's everything we had to do for part A. Now, for part B, we want to repeat this procedure, but in a slightly more complicated manner, as we will see shortly, because we will see that this delta, it exceeds the yield limit for one of the materials. So we need to be more careful. So let's say this was part A. Now, for part B, we basically repeat the same thing. We calculate gamma 1 and gamma 2 and see where we stand if we have delta of 26. So let's say gamma 1 is delta divided by H1 again, as we did before. Gamma 2 is delta divided by H2. Now, if you calculate gamma 1, that would be 6.2 times 10 to minus 4, which is still less than 7 times 10 minus 4. So we are still in elastic regime for the first one. But for the second one, we will get 9.6 times 10 to minus 4, which is no longer smaller than 9 times 10 to minus 4. So what happens is that for member 1, we are still elastic. So tau 1 is still G times gamma. You can use that elastic relationship, and that gives you 53.14 megapascal. But for the second one, tau 2, it's already plastified, and it has reached the yield stress. So tau 2 would be simply the yield stress of member 2, that is 45 megapascal. Okay, so if you remember, here delta was 13, here delta is 26, right? So there is a factor 2 basically. As you can see, when it is elastic, you get a factor 2 in your stress 2 for member 1, but for member 2, because we entered plasticity, you get something less than 2 times 24, right? If it was fully elastic, you would have gotten 48. But because we reached plasticity, that's that. So now you take these again, and then you calculate V using the same formula that we had up here. V is tau 1 plus tau 2 times area. So it's tau 1 plus tau 2 times area, and that gives you, if you calculate it, it gives you 441.6 kilonewton, which again, if you compare this with this one, is less than 2 times that, right? Okay, so for part 2, the shear force you need is 441.6 kilonewton, and that is, again, less than 2 times 227.6 kilonewton, because we know one of the materials, or the material 2, it has gone plastic, okay? All right, so that's the answer to part 2. Now, suppose that you slowly increase this V. What is the value of the force at which yielding starts? Okay, so here is the question. Remember, if we apply 227.6 kilonewton, we know it's fully elastic. If we exceed that to 441.6 kilonewton, we know one of them is plastified. The question asks you, what is the maximum force you can apply and still both of them are elastic. Okay, at which point does it start? We know it's less than this, because if we apply this, we are already in the plastic zone. So we are looking for a number between these two where the plastic or yielding starts. And by the way, if you remember, we call this thing, or this loading that I'm going to talk about, this is the maximum elastic load. This is exactly what we want to calculate. So maximum elastic load. All right, so how do we do this? We just, we already know that for this much force, the first one is elastic, and the second one got plastic, right? So the second one is the critical material. So we should find out at which point, or for how much delta, this one starts to yield, and then insert that value. All right, so tau2 is 45 megapascal for for gamma 2 of 9 times 10 minus 4. Okay, now at the onset of instability, at the onset of plasticity, we are here. Okay, so what we want is to have this shear strain as delta divided by height of the second material, right? So we are looking for this delta. What is this delta that this thing starts? Okay, so this would be delta divided by 2.7 centimeters, and then from this you can calculate delta to be 224.3 micrometers. And we call this delta elastic. Okay, so which makes perfect sense. So again, if delta was 13, it's fully elastic. If it is 26, already one of them is plastic. This is exactly the value. So at 24.3, it starts to plastify. Okay, and then all you have to do now is, for this particular value, you need to calculate the stress in both members, add them up. So in member 2, for this value, the stress is 45 megapascal. But for member 1, then for this one, you need to calculate your stress using your diagram. Okay, so from this one, you can calculate gamma 1, which is now this delta E divided by H1. And that gives you 5.786 times 10 to minus 4. All right? And then from that, you can calculate tau1 using G1 gamma 1. Right? And if you do that, for tau1, you get 49.6 megapascal. Okay? So now tau1 is 49.6 megapascal. Tau2 is 45 megapascal. You add them up, you multiply by the area, and you get your force. So here, all you need to do is to say V is now that, again, tau1 plus tau2 times area. And this tau1 and tau2, these are the ones that I'm writing with, let's say, with this purple color. And if you do that, you get 425.7 kilonewton. Okay, so this is your maximum elastic load. And as you can see, this number is somewhere between these two. Okay, it's somewhere between 227.6 and 441.6. All right. Now, the next question is, what is the maximum V that one can apply? So maximum V, remember this was maximum elastic load. What we want to calculate next is maximum plastic load. It gets a little crowded, but I think you can follow. It's not too bad. So what's the maximum plastic load? That's what we want to do. That's pretty easy, because that means at this point, both of them are plastified. So that V would be tau Y, so the yield limit of the first material plus the yield limit of material 2 times area. Okay, and that would be 472.5 kilonewton, which also makes sense. So it's more than this, and that's definitely more than this. Okay, so this is the maximum load you can apply. Okay, because these flatten, basically. The last thing the question asks you is plot V versus delta, when delta is varied from 0 to 50 micrometers. Okay, so you can do this. Before doing that, by the way, I want to just tell you how much delta you need for this. So in order to get to this value, the corresponding delta, you know, this one is already plastified, but in order to know what is the delta for that one, we need to use this, right? So you would say this delta, and let's call this delta P. Remember, we call this one delta E. So we call this delta P. Delta P divided by H1 is gamma 1. But now gamma 1 is 7 times 10 to minus 4. Okay, so this is the yield strain. Okay, now if you do that, this gives you delta P of 29.4 micrometers. Okay, which again, it makes sense. So at 13, everything is elastic. At 24.3, this one plastifies. And then if you continue at 29.4, both of them plastify. Okay? So when you want to draw your diagram, V versus delta, all you have to do is to kind of identify these numbers. So you would have a plot like this. There is V, there is delta, and then here you would have, let's say, your elastic regime. Then you have a slope decrease, and then you have your flat line, and then these numbers would correspond to what I just said. So this would be 24.3, this would be 29.4, and this is, let's say, all the way to 50. Okay? So this is how your diagram would look like. I want to find a space to draw it here, but I don't know if it's possible. Okay, let me try the following. I draw it black and thick here. So it's gonna look like this. At the beginning, you have your elastic regime. So both materials are elastic. Then you have this regime where material 2 is only plastified. And then again, if you think of this axis to be delta, this would be delta E. This would be delta E, and this would be delta P. And we calculated them. So delta E is 24.3, and delta P is 29.4. Okay? And then after that, your V would be just flat here. And the corresponding forces, we also calculate them. So this is VP, maximum plastic load, and this is VE, maximum elastic load. Does that make sense? All right. So, okay, it got a little crowded, but you get the idea. All right, so we jump to the next question. Here we have a frame subjected to the load of 4 kilonewton, which acts on member ABD at D. The allowable shear stress for the material is 40 megapascal. Pin C is subjected to double shear, whereas pin D is subjected to single shear. Determine the required diameter of the pins at C and D. Okay, all you have to do is to basically draw your free body diagrams for each piece of these. For the horizontal piece, here you have E, and then you have the force EY. Then at C, you have your T. Remember, BC is a two-force member, so you get T on both ends. At D, you get dx dy, that we don't know what they are. But whatever they are, their reactions would be in this other member. So you would, let me just draw it in the opposite direction, that it makes more sense. So let's say this is dy and dx. And then maybe this is dx is the opposite of what we had there, and dy is the opposite of what we had there. And the force 4 kilonewton, we just apply it here. It doesn't matter on which of these you apply that. You should just apply it. You can also apply it 2 and 2 or something like that. Eventually, you would see its influence in the D's. Okay, so, and then you would have T here and AX and AY, which we don't need. Okay, so what you need to do is to write your equilibrium equations for each of these members. And for each of them, you can just write your equilibrium of forces or moments. So I'm going to write that. Let's say for the upper member here, ECD, EY plus dy minus T sinus 45 degrees is 0. That's the vertical equilibrium. Then you have T cosine 45 degree minus minus dx is 0. Then for the other one, you have, well, you can write EY times 2.5 minus T sine 45 times 1.5 is 0. So this is basically your equilibrium of moments with respect to A. This is equilibrium of forces in x direction for the upper member. This is equilibrium of forces in the y direction for the upper member. And then for the side member, you can also, let's say, write your equilibrium of moments again with respect to A. Okay, so you get 4 times cosine 45 times 3 minus 3 dx plus T cosine 45 times 1.5 is 0. Again, this is now also equilibrium of moments with respect to A, but this is for, let's say, for ABD. This one is for entire structure. All right? So you have four equations, 4 unknowns. You get T to be 8 kilonewton here, dx to be 4 square root of 2 kilonewton. That's that, which is 5.657. And dy is 1.6 square root of 2 kilonewton. That's 2.263. And EY is 2.4 square root of 2 kilonewton. That is 3.394. All right. So you have these. Now, we want to calculate the shear stresses in pins D and C. In pin D, the total force of the pin would be square root of dx squared plus dy squared. Okay, that gives you 6.093 kilonewton. Now, shear stress in D is that total shear force divided by area. It's a single shear pin. In pin C, that's a double shear pin. It's therefore half of the shear force divided by area. So here, if you do that, therefore you get AD to be 0.152 10 to minus 3. Here you get AC to be 0.1 times 10 to minus 3, and therefore you can calculate the required radius or diameters for that matter. So this would be 6.963 millimeters, and this would be 5.641 millimeters, and therefore this gives you the diameter of 13.93 millimeters, and this gives you the diameter or the required diameter of 11.28 millimeters. All right, so this is the next question. We have one final question to look into together. So you have the rod ABC of radius C embedded into a medium where distributed torque reaction varies linearly from 0 at C to T0 at B. The coupled forces P are applied to the lever arm. Assume the rod is made from a material having a shear modulus of G. Determine the value of T0 for equilibrium. Okay, so you apply this much torque. You know there would be a linear distribution of internal shear, but you don't know how much of that maximum you need to get equilibrium. So you calculate that, and then based on that, you calculate the angle of twist. All right. So it's very similar to what we have done before for this sort of problem. So all you need to do is to just be careful, draw your coordinate system. So here you would start from point C. You start your coordinate system X, and then let's say based on that coordinate system, you would have a TC here that's external, which by the way, it's 0 here. There is nothing at the end, but I just put it there for simplicity. And then you would have your, let's say, Tx. This is T as a function of X. Okay. That's your internal torque, which I also draw it counterclockwise according to our convention. And then inside that member, you have this little clockwise torques. Okay. So the first thing you want to do is to write equilibrium. And if you write equilibrium for this thing, you can immediately see that, let's say, Tx with a plus minus integral from 0 to x of T dx is 0, right? I mean, there is no Tc, otherwise it would also enter that equation. So that tells you Tx is the integral from 0 to x of T dx. Now, what is this T? You see, it's a linear distribution from 0 to L over 2. Okay? So T as a function of x is the slope of that line times x. The slope of the line is T0 divided by L over 2 times x. Okay? So if you insert that, you get Tx equals integral from 0 to x of T0 divided by L over 2 x dx. So that gives you 2T0 divided by L integral from 0 to x of x dx. So that gives you x squared divided by 2. So you get T0 divided by L x squared. Okay, so this is your internal torque. Now, that internal torque from B to A, it's constant, right? At B, it would be T at x equals L over 2, right? So basically, all you have to do is to say T at x equals L over 2 is equal PD, which is the external torque that you apply here. Okay? So that's all you have to do. So basically, T at x equals L over 2 must be equals PD. At at x equals L over 2, and you would get T0 L over 4 equals PD, right? You get, if you put here L over 2, you get L squared divided by 4. L cancels out, so you get this. So therefore, you know now that T0 is 4PD divided by L. Okay, so this was the first question. The first question was, what's T0 such that you would have equilibrium here? Now, the second part is just integrating our relationship to get the angle of twist. So angle of twist at A, so that was, let's say, part A, and part B, you want angle of twist at A, or rather angle of twist of A with respect to C. That would be A with respect to B plus B with respect to C, which is otherwise just phi, let's say, from B to A plus phi from C to B. So pay attention that these, both of them, they follow our plus direction of x coordinates. Okay, so there is no complication there. Now, all you have to do is to just integrate, let's say, from B to A, the relationship that we had, T dx divided by Gj, plus integrating from C to B, T dx divided by Gj. All right? So now, between B and C, or between C and B, it's the first part. We know exactly the equation for T. Between B and A, T is just constant, okay, which is the same as, you know, PD. So that's the relation we have. So we would have integral from B to A, and then again from B to A, x would go from L over 2 to 2. T is simply PD, which, by the way, it's no surprise. So this is essentially T at x equals L over 2 that we discussed before. Dx divided by Gj plus, from C to B, this goes from 0 to L over 2. Now, Tx is just what we had up there, dx divided by Gj. And as I mentioned, this Tx here is nothing but just what we had there. If you integrate these together, you would end up with a relationship which looks like, okay, I jump over the integral, but you get 4 over 6 PdL over Gj. Also pay attention that, you know, because at this point we know the relationship for T0, we also use it here, okay? So we know that T0 is 4 PD over L. Okay, so you get this relationship, and all you have to do at the end is to remember that J itself is, I mean, if you want to, it's pi over 2 c to the power 4, okay? And if you do all of that correctly, your phi would be 4 p d L divided by 3 pi c to the power 4 times G. Okay? All right, that's that. That was the last exercise for today.